Hello and welcome back to Chapter 3. Today we're going to look at 3.3, which deals with increasing and decreasing functions and the first derivative test. So our first objective will be to determine the intervals in which a function is either increasing or decreasing, and then we're going to apply the first derivative test and find relative extrema of the function. So let's go ahead and take a look at the increasing and decreasing functions. By definition, a function is increasing on an interval if for any two numbers, and we'll call them x1 and x2, if f of x1 is less than f of x2, then we say that the function is increasing. A function is decreasing on an interval if f of x1 is greater than f of x2. So as we're going from left to right, if the graph moves up, our function is said to be increasing. So something like this scenario right here, as we're going from left to right, our function is increasing. If I go from left to right and my graph is going down, then we say our function is decreasing on this interval. If we have a flat portion of the graph or no change, then we say that our graph is constant on that interval. And we have a little test to determine whether a function is increasing. And it says if f is a continuous function on a closed interval from a to b, and it's differentiable on the open interval, if the derivative of f is greater than 0, then f is said to be increasing. If the derivative of f is less than 0, then f is decreasing. And if the derivative of f is equal to 0, then we say our function is constant. So let's look at example 1, where we have to find the open intervals on which the function f of x equals x cubed minus 3x squared is either increasing or decreasing. The first thing we're going to want to do is we're going to want to take the derivative. So f prime of x equals 3x squared minus 3 halves times 2 is going to give me 3x. Then we're going to want to take and set this equal to 0 so that we can solve for our critical numbers. So what we're going to end up with is I can factor out a 3x, and that leaves me with x minus 1 equals 0. And my critical numbers then are going to be when x equals 0 or when x equals 1. And because the derivative of f has no points in which the function cannot exist, our only critical numbers in this case are going to be 0 and 1. And if you think back to pre-calc in Chapter 2, when we were trying to graph functions and come up with whether or not the function was increasing, we created a table. We're going to actually do the same thing in Calc. So when I set my table up, I'm going to set up a test interval. I'm going to look at a x value, which I'm going to pick, and it comes from within my test interval. Then I'm going to evaluate f of x. I'm going to look at the sign. And this is all we had to do in pre-calc. Now in calc, we're going to add one more element to it. We're going to have the conclusion column or row. So based on my critical numbers here of 0 and 1, I'm going to set these up in order of increasing order. So 0 is going to come first. And I'm going to look at everything from a negative infinity to 0. Then I'm going to look at the interval from 0 to 1. And then at the interval from 1 to a positive infinity. The next thing I'm going to do is I'm going to go in and I'm going to pick some value between negative infinity and 0. And in this case, I'll do a negative 1. On the interval from 0 to 1, I'm going to go in and pick a number between 0 and 1, and that will be 1/2. And from 1 to infinity, I'm going to pick 2. Then what I'm going to do is I'm going to go and evaluate, and this should be f prime of x, And when I evaluate f prime of x at x equals negative 1, I get 6. F prime of x at a positive 1/2 will give me a negative 3/4. And an f prime of 2 is going to give me 6 as well. Now the sign is going to come from whatever the sign of this row here is, and we end up with a positive number, a negative number, and a positive number. So what I can conclude from that is that my function is increasing, and from this point forward I'm just going to draw an upward arrow. Here my function is decreasing, or a downward arrow, and then I'm increasing again. So I'm increasing on the interval from a negative infinity to a 0, and from 1 to infinity, and I'm decreasing on the interval from 0 to 1. And if you take a look, you'll see that we have a function that was increasing, then decreasing from 0 to 1, and increasing again. This will confirm what we just came up with in our previous table. Now we do have a set of guidelines for finding intervals on which a function is increasing or decreasing. And if the first thing we have to do is we have to identify that the function is continuous on your interval from a to b. Then we want to find the open intervals where f is increasing or decreasing, and we're going to use the following steps. Step 1 is to locate your critical numbers and use these numbers to determine your test interval. Remember, critical numbers are going to be like setting your derivative equal to 0, or anything that x cannot be. Then we're going to determine the sign of the derivative at each test value on the intervals. Then we're going to determine whether or not the function is increasing or decreasing on each interval. And the best way, I think, to do all of this is to create your table. If you create your table, it just kind of helps you keep things a little bit more organized. On a side note, however, a function is called strictly monotonic on an interval if it's either all increasing or all decreasing on the entire interval. And an example of this would be something like f of x equals x cubed. You'll see that we are increasing, and we're going to continue to increase. Now in this case here, we have something that may look monotonic because it does increase here and here. However, we have this flat region right here where we are constant. Because this is constant right here, this is not strictly monotonic. And now we're going to look at the first derivative test. The first derivative test is going to help us locate relative maximum or relative minimum points once we've identified where the function is either increasing or decreasing. And we're going to do that by letting c be some critical number. And if we notice that the derivative changes from negative to positive at this critical number, then we have a relative minimum. And you get that relative minimum because your slope is going from negative to positive, which is going to give you the minimum right here. However, if your derivative changes from positive to negative, then we have this point right in here where we have a relative maximum. Now, if both sides of a critical point are either negative, so I have something like this, and then I have my critical point C, and then I have another negative slope, or I have a positive slope, my critical value C, and another positive slope, then this tells us that we have neither a maximum nor a minimum. So this is just another iteration of the first derivative test. Again, I have a negative slope, and I'm changing to a positive slope, which tells me I have a critical point, which is a relative minimum. Here I've got a positive slope. It's changing to a negative slope at that critical point, which tells me I have a maximum. And here I have two positives and two negatives on either side of my critical point. Therefore, I have no relative min or max around that critical point. Example 2 then says that we are to find the relative extrema of the function f of x equals 1/2 x minus sine x on the interval from 0 to 2 pi. Please make note that we are not including either 0 or 2 pi because of that set of parentheses. So we're going to start out by finding the derivative of f, which is f prime of x. And the derivative of f is going to be 1/2 minus the cosine of x. And I'm going to set this equal to 0 and solve. So I end up with the cosine of x equals 1/2. Well, on the interval from 0 to pi, or 2 pi, I know that my critical numbers are going to, of x are going to be pi over 3 and 5 pi over 3. If you plug either one of these numbers in here for x, you'll see that you get the positive 1/2. And again, I'm going to go back and say, or ask myself, is there any point on the derivative function, and this should be the derivative, where this function cannot exist? And the answer to that question is no. So these here are going to be my only critical numbers. So because these are my critical numbers, I'm going to go ahead and set up my test intervals. So my test intervals then are going to be from 0, because I'm going from 0 to 2 pi. So I have 0 to pi over 3. Then I'm going to look at pi over 3 to 5 pi over 3. And from 5 pi over 3 to 2 pi. Then I'm going to have a test point, so I'm just going to put TP for test point. I'm going to evaluate f prime of x at that test point. I'm going to look at my sign, and then I'm going to make some conclusions. So my test point from 0 to pi over 3 is going to be pi over 4. From pi over 3 to 5 pi over 3, I'm going to pick pi. And from 5 pi over 3 to 2 pi, I'm going to pick 7 pi over 4. When I evaluate my function of the derivative at pi over 4, I end up with 1/2 minus the cosine of pi over 4, which is 1/2 minus the square root of 2 over 2. And if you evaluate that, you'll see that you get a negative number. If I plug in pi, then I end up with 1/2 minus a negative 1, which becomes plus. So this is going to give me a positive sign. And here we're going to end up with 1/2 minus the square root of 2 over 2, which again is a negative number. So what I notice now is that I'm going from a negative slope to a positive slope, so I'm going to be decreasing, then increasing, and then decreasing again. So based upon my increasing and decreasing values, I see that I'm decreasing and then increasing and decreasing again. So this tells me that I have a minimum at x equals pi over 3, because it's kind of like this number here is the critical point. And then I have another critical event happening here. That's where I'm going from a positive slope to a negative slope. So this is where I would have a maximum, and that's going to occur when x is equal to 5 pi over 3. And again, we do not include the 0 or 2 pi because I have parentheses and not brackets. And here's the graph that will confirm what we just found. We have a relative minimum at pi over 3, which is right here. we have a relative maximum at 5 pi over 3. And when we look at our graph confirms what we were able to solve for algebraically. And our last example for the night says to find the relative extrema of f of x equals x squared minus 4 to the 2/3 power. So again, we're going to start out by evaluating f prime of x. And we see that we're going to end up with 2/3 times x squared minus 4 times the derivative of the inside, which is going to give us 2x. And I'm just going to simplify that into 4x divided by 3 times the quantity of x squared minus 4. And I'm going to set that equal to 0. Oops, and I realized I forgot to apply my entire chain rule because I should have had a negative 1/3 here, which means I should also have a negative 1/3 right there. So if I rewrote this, I really have 4x divided by 3 times x squared minus 4 to the 1/3 of the cube root power equals 0. Now the reason I wanted to rewrite this is because if I go ahead and set this equal to 0 and solve for x, I'm able to identify the fact that x equals 0, because if I multiply both sides by this denominator, that's going to clear it out of here, so then I'm left with 4x, and 0 times this stuff is going to give me 0, so I have 4x equals 0, therefore x equals 0. So that's taken care of. Now, one other thing we have to look at though, is there any values of x that are going to make my denominator undefined? And in this case, there is. If I take and make my x value either a positive or negative 2, that's going to make this whole piece go to 0. And because of that, those then are considered critical numbers as well. So when I go to set up my table, I need to include 0 and plus or minus 2 on my test interval. So let's go ahead and do that right now. So I have a test interval, and I'm not limited on any starting or ending points. So I'm going to go from a negative infinity to a negative 2 because I'm going in increasing order from smallest to largest. Then I'm going to go from negative 2 to 0. Then I have 0 to a positive 2, and then 2 to a positive infinity. I'm going to go and pick a test point. So I'm going to go negative 3, negative 1, 1, and 3. I'm going to evaluate f prime of x. Then I'm going to look at the sign and then make a conclusion. So my f prime of x value is going to give me a negative 2.2, we'll say 3. When I evaluate at a negative 1, I end up with 0.924. When I plug in a positive 1, I get a negative 0.924. And if I plug in a positive 3, I get 2.33. So now what that tells me then is I have a sign change. I'm going from negative to positive to negative to positive, or I'm decreasing, increasing, decreasing, and increasing. So if I kind of sketch this out, I'm going down, up, which means that I have a max and 2 mins here. So my max is going to occur when x is equal to 0, and my min then is going to occur when x is equal to plus or minus 2. So this is going to include the notes on 3-3. We will have more discussion on this in class tomorrow. And your math fun fact for the day is a Foxtrot comic strip. So on that note, have a good night, and we'll see you tomorrow.